All right, so today we're looking at topic 3, the spectroscope, new meanings in light. So the spectroscope, it was one important technological advance that helped us learn more about the stars and the composition of stars. And we're going to learn about something called the Fraunhofer lines. So spectral lines. So when we saw back last week, we were looking at Isaac Newton and how he passed a beam of sunlight through a prism to produce a spectrum of colors. So his experiment showed that sunlight, which is white light, is actually made up of all colors. So a spectroscope is a device that produces a focused spectrum. If you pass a beam of light through a narrow slit before sending it through a prism, that resulting spectrum shows much finer detail. And in the 1820s, this man here, Joseph von Fraunhofer, he was a German optician, he used a spectroscope to observe the sun's spectrum. It had very fine prisms, and he noticed hundreds of dark lines in the sun's spectrum. So that's what we see here, all of these darker lines. It's also called the solar spectrum, and those dark lines are called spectral lines. So I'm going to pause here. So spectroscopy, the science of color. So chemists knew that the vapors of different elements, they give off different colors when they're heated to incandescence, meaning hot enough to glow. So for example, sodium vapor, it gives off a yellow color. Mercury gives off a bluish color. So like we saw in the video, the two scientists, Gustav Kirchhoff, a German physicist, and Robert Bunsen, he was a German chemist, they heated various chemicals to incandescence and they examined their light through a spectroscope. And they discovered that not all of the colors of the rainbow were present. They saw that each spectrum was a series of colored lines with black spaces between them. So each element has a set of spectral lines different from the others. So for example here, this is what it looks like for hydrogen when hydrogen is heated. So each spectrum was unique and it could be used to identify the element. So these results, they helped found the science of spectroscopy as part of chemistry. And it's basically the study of the spectra, which is the plural form of spectrum. So there's 3 types of spectra that were discovered. So each element produces a unique spectral pattern. The first type is the emission or bright line spectrum. So you take a gas, you heat it at low pressure, and it's going to produce a spectrum light. That's only a set of bright lines against the black background. That's called emission or bright line spectrum. Next is a continuous spectrum. So if you take a solid, liquid, or a gas and you heat it at high pressure, the resulting spectra, they contain all the colors blending into one another. That's called a continuous spectra. It's a rainbow that you would see like in a rainbow in the sky. And then we have the absorption or dark line spectrum. So you take that gas, it's heated at a high pressure, or it's a heated solid or a liquid. You pass it through a cooler substance, and then we see the continuous spectrum here. One second. So here then, when we're looking at that spectrum there, this is called an absorption or dark line spectrum. It's a continuous spectrum with those dark gaps between colors. It's the same type of phenomenon that Fraunhofer saw when he looked at the solar spectrum. It's because of the gas that the light passes through, it absorbs or removes some of the colors of the light in the spectrum. So next, we're just looking at diffraction gratings. So like we saw, the spectroscopes, they were using prisms to split the light into a spectrum, but there's a different way to split the light. It's by using a diffraction grating instead of a prism. So basically, it's a device that's made of thousands of closely spaced slits. And then when light passes through those small openings, that are very close together, a spectrum is produced. All right, and the reason that happens, so here, for example, we can see the slits, is that because the light waves, they bend around corners, they diffract, and then they pass each other, causing interference. So they can cancel each other out or reinforce each other. And this spectrum that's produced by a diffraction grating, it has much better detail in it than a spectrum from a prism. So here we can see on both sides, it's split into a spectrum, but it's showing on both sides there. So astronomers and spectroscopy, so each element like hydrogen, helium, calcium, sodium, as a low pressure gas, it produces a unique pattern of those spectral lines. Those lines are then used to identify different gases found in light sources. So each set of spectral lines, it belongs to one light source only. Then as light passes through a gas, parts of the light are absorbed. And that's what's creating the dark lines in the spectrum. So then, if the sun's spectrum also has dark lines in it, it must mean that sunlight passes through some gases. So the conclusion is that gases in the sun's atmosphere, they're absorbing the light that is removed from the solar spectrum. So astronomers can use spectral analysis. So basically, if the dark lines placement in the solar spectrum, if it matches the bright lines produced by various elements, then those elements are present in the sun's atmosphere. So for example, here are some different elements. We have hydrogen, helium, sodium, calcium, and we have mercury, and then we have the sun at the bottom here. So you can use like a ruler or something like that to kind of match up those lines. So for example, here's hydrogen. You can match it here with the sun. Same with this one here. But using a ruler for better measurements, we can see which of these elements are present. All right, we can also see helium here and here, here and here, and so on. We can also use something called a Doppler effect. So spectroscopes, they're used to identify the chemical makeup of the atmospheres of celestial objects, but they can also tell us how fast a celestial body, such as a star, is moving towards or away from us. And that's called a Doppler effect. We can use this effect. It's the phenomenon that the observed frequency of a wave, it changes if the source of the wave and the observer are moving towards or away from each other, from one another. So if we look here, the Doppler effect, like if we have a fire truck and its sirens are ringing, it's not moving, the siren sound, it has the same pitch in all directions because the sound waves are uniform. Okay, but here the truck is moving, it's moving to the right. So when the fire truck is moving, the sound of the siren seems to change in pitch. It's becoming higher as the truck moves towards the observer and lower as it moves away from the observer. So that's the Doppler effect. And that can be used in spectroscopy. It can be used to measure the speed and direction of light-emitting objects like stars. So when we're looking at sound, the sound waves from a moving object, they differ in pitch. The light waves.
I am so sorry about the chat.
So the light, so like I was saying, the sound waves, while the sound waves from a moving object, they differ in pitch, the light waves from a moving object will differ in color. So if a star is approaching us, its wavelengths of light become compressed, and the dark lines in the star's spectrum, they shift toward the shorter wavelength end of the spectrum, which is the blue end. So here. If the star is going away from us, the spectral lines will be redshifted. Shown here, they're moving towards the longer wavelength part, which is the red end of the spectrum. Okay, so this stationary star, spectrum A, it's a stationary star. If the star is moving towards us or towards Earth, we can see it becomes blue shifted. So the lines are shifting to the blue end, and if the star is moving away, the lines are shifted to the red end. Okay? Any